Okay, it's time to bring it home here for section 3.2 with our last objective, which is dealing with what's known as Heron's area formula. So this is an alternative way to find the area for an oblique triangle, and it's specifically used when we know the lengths of three sides, but don't know any of the angles between them. So it's a little bit different. It's kind of like the way that law of cosines is to law of sines. Heron's area formula is to the previous area formula that we saw in section 3.1. It's pretty straightforward, all things considered. The way that we're going to go ahead and find Heron's area formula is by using law of cosines and then adapting it with the work that we've already done in terms of our formula for the area of a triangle, that 1/2 the base times the height. In this case, we're simply working off of, okay, we only know the length of the sides. We know that's enough information to find the angles between them. That's what law of cosines has shown. But if that's the case, we can actually go ahead and establish an additional formula that skips over finding the angles between the sides and goes straight to finding the area using the work that we've already done. So Heron's area formula is as follows. If you have a triangle with side lengths A, B, and C, the area for that triangle is equal to the square root of S times S minus A times S minus B times S minus C, where S is defined as the perimeter of the triangle divided by 2. A plus B plus C all divided by 2. So in this case, it's kind of a little bit funky, but this is adapted again from the work that we've already done. In this case, this use of S being A plus B plus C over 2, well, you can kind of see where that's reminiscent of the 1/2 that we normally see as part of our area formula. In this case, the subtraction of A, B, and C is fitting into the different variations for depending upon which angle you're working with. There's a lot more going on in the background, and the proof is a little long-winded, so for once, we're just going to go ahead and take this at face value. This is one that should be fairly straightforward to memorize. Just don't forget how you find S. It is not the perimeter, it's the perimeter divided by 2. So long as you can commit that to memory, you should be good to go, because the rest is a pretty straightforward pattern. S times S minus A times S minus B times S minus C, and then take the square root of that value. We don't have to worry about plus or minus, because since it's an area, we know it'll be positive. And the only last piece you need to note here is to make sure to include correct units, and because this is area, it'll be square units that you need to include. Let's go ahead and tackle a specific example. Let's say we have a triangle whose side lengths are 43, 53, and 72 meters. This is going to be straightforward. We're simply going to start by finding S, and then once we have that, we're going to substitute in our formula and evaluate as quickly as possible. So let's go ahead and pop over to the notepad to take a look. We'll begin by finding S, so that's going to be the sum of all three of our lengths, then divided by 2. Let's switch to black for this. So this will be 43 plus 53 plus 72, all divided by 2. Alright, sum of the first is 96 plus 72, so 168 over 2, which, correct me if I'm wrong, should be 84 here. So now we have the length for S. We can go ahead and substitute into Heron's formula. Area is the square root of S times S minus A. So we'll go ahead and do this as 84 minus 43. S minus B, 84 minus 53, times S minus C, 84 minus 72. Let's go ahead and do a little bit of house cleaning here. So this will be 84 times 41 times, oops, no, that's right, yep, times 31 times 8. In this case, this is one where just looking at the numbers that I've got here, I've got at least a couple primes. Things aren't going to come out super clean here. So no matter what I do, this is going to be an approximation here. Oh, that shouldn't be 8, that should be 12. Get my numbers backwards. Okay. Taking a look at this and taking an approximation of this product, we're going to get, and if we round it to 2 decimal places, an approximation of 1,131.89. And then don't forget the original context. These were meters, but since this is area, this is square meters as our final result. You can see that when you compare it with some of the earlier work that Heron's formula is actually really, really nice. But here's some things to kind of consider. We would only ever use Heron's formula if we already knew all 3 side lengths in advance. In this case, if I knew 2 of the side lengths and maybe 1 angle, I would probably look to use my different area formulas that we saw previously. That's the kind of thinking process we need to go through as we tackle problems of this type. And actually, there's a little bit of information kind of included on sort of critical thinking, or you might even consider it like flowchart, as to how you should take on specific area formulas included as part of our work in the slides themselves. I'm going to go ahead and pull that up so you can kind of see for yourself. Let me swap back over to the slides here. The standard formula that we use for area that would be really nice to use is 1/2 the product of the base times the height, but this would only really apply if we could easily find the value for our length, for our height, our altitude. In the cases where we can't, which would more often than not be an oblique triangle, we would use the following area formulas first if we can. This is when we know 2 side lengths, and in this case the angle measure between them. We would prefer to use these. 1/2 b times c times the sine of a, 1/2 a times b times the sine of c, or 1/2 a times c times the sine of b. If you don't know any angle measure, then you can go ahead and apply Heron's formula, assuming you know all 3 side lengths instead. So this is kind of an order of preference. Even though they mentioned that this is just the 3 different formulas, this is also the way that you should try and approach it. If possible, use standard form. Barring that, use one of our 3 formulas that use the sine of a known angle. Barring that, use Heron's formula that uses all 3 side lengths. We wouldn't want to use Heron's formula if one of our side lengths is an approximation, because we're going to have several orders of approximation error as a result. If you approximate A, B, or C, then you've also approximated A, and you've also approximated all 3 of these differences. You have a high probability of being pretty far off the mark when the errors are compounded like that. So only use Heron's area formula if you already know all 3 side lengths. That's just kind of a general way to approach problems of this type that you should keep in mind going forward. Alright, that's going to do it for section 3.2. I'll see you guys next week for the wrap up here of module 4 with the remaining lectures.